with a small recap of whatever we have covered so far, because there was a bit of a clutter along the way, because there are too many things that we have discussed with flexural members. So therefore, I wanted to do a little bit of summary. So we had started with the laterally restrained beams. I did not really mention it at that time because it didn't really. In order for me to explain what is laterally restrained beam, I would have been required to explain what is laterally unrestrained beam and what is the consequence of that. So now I suppose you must understand what is laterally restrained beam. So laterally restrained beam is the beam that cannot undergo lateral torsional buckling. So laterally, it is prevented against movement. Okay. Can somebody just type a message and say that, let me know if you are able to follow me, what I'm saying, you're able to hear me clearly. Okay, good. All right, so starting with laterally restrained beam, then laterally restrained beam has only one limit state, that is limit state of yielding, right? So you have only one limit state, that is limit state of yielding. And in this, we had a discussion about compact and plastic sections. And another group was semi-compact sections. And based on which type of section it is, we discussed that we can use MZ, or we can say MP, or otherwise we may use only MY as the capacity of the cross section, right? Everybody can recall it, right? So, and this classification is basically based on the possibility of undergoing local buckling. So if the cross section is susceptible to undergo local buckling beyond yielding, then we will call it semi-compact and we can use only MY capacity. If it is really, it's made of thick cross sections, thick plates, then it can undergo large plastic deformations. Then we can classify as compact or plastic, and then it can carry as much as MP, right? And you remember the difference between MY and MP. Good. So this is basically governed by the susceptibility to local buckling. Okay. Then we started talking about the lateral torsional buckling, so which is possible only for laterally unrestrained beams. All right, so the beams that are laterally unrestrained, they can actually move sideways when the compression, when the flexural load is applied. Half of the cross section will be under compression and half of the cross section will be under tension. So the part that is under compression would want to move sideways, right? And that is how we would have laterally unrestrained beam, and that beam can undergo lateral torsional buckling. So then you have two limit states. Limit state of lateral torsional buckling. Okay, and of course yielding still exists. That possibility is still there. Okay, so since both these possibilities are there, so the idea for the design calculation for a laterally unrestrained beam was as follows. So if it is laterally unrestrained, but depending on whether the beam is bending in the minor axis, whether the beam cross section is kind of a hollow cross section instead of open cross section. So depending on what cross section it is, what is the distance between the lateral supports, based on that, you can there may be possibility where you can rule out the chances of lateral torsional buckling, and you just need to consider about yielding. Okay, so then we had discussed this plot, moment capacity, and on the horizontal axis we were plotting the slenderness value. we call it lambda LT. Okay, so lambda LT is basically a representation of your lambda LT is a representation of the length or the distance between the lateral supports. Okay, so if the lateral supports are farther apart, your beam is more susceptible to undergo lateral torsional buckling. And what we saw was that the behavior actually looks somewhat like this. So at a particular point, this may be your my value or MP value, depending on what type of cross section you have. And starting from there, you go somewhat like this. And then there were two curves that we had discussed last time. One curve was for the two different imperfection factors. So if it's a hot rolled section, you had alpha is equal to 0.21. And if it's a welded section, then you had alpha is equal to 0.49. So more imperfection means lower capacity. All right. And what the code said was that if your slenderness lambda value is up to 0.4, I suppose that was the value. I'm not quite remembering that. I think it was 0.4. So as long as your lambda is less than 0.4, you don't have to consider any drop in the capacity because of the slenderness effect or because of the lateral torsional buckling. You can take full capacity, which was my or mp value, right, as if it was an unrestrained, as if it was a fully restrained beam. Okay. In addition to that, just further elaboration. So in which cases, even though the beam may be unrestrained, in which cases you don't have to consider the effect of lateral torsional buckling. So the beam is unrestrained, but you may still consider only this yielding limit state in following conditions. One, if the beam is lambda is less than 0.4, less than or equal to 0.4, equal to is also okay. Second point, your cross section is hollow, right? So if it is made of this kind of a cross section, okay, so that's a hollow cross section. This kind of a cross section, you or some other cross section that you can think of, any hollow shape, which is not an open cross section, any closed hollow cross section or a circular cross section, that will be even if it is bending about the major axis, you don't have to worry about it. Third one was the bending in minor axis. All right. So if the cross section, if the beam is bending about its minor axis, then basically what it means is that its resistance against bending in major axis is very high, right? And that is the lateral direction. Major axis is the lateral direction, right? So in the lateral direction, it is not likely to buckle because it has a very high stiffness in that direction, correct? So if these conditions are true, then you don't have to consider the possibility of lateral torsional buckling. Only if none of them are met, if even one of them is satisfied, then you don't have to consider lateral torsional buckling. If none of them are met, then you have to consider the possibility of lateral torsional buckling, but that is quite commonly because that is the most efficient way of using a beam, right? So most likely cross section for flexural members is the most likely cross section is an I section, right, for flexure. And if you have an I section, that is the case where, and if the lateral supports are not very closely spaced, then you have to consider lateral torsional buckling effect for this kind of a beam. Okay. Some additional conditions. If the beam is supporting a slab, let's say if I have a beam and it is supporting a slab, okay, the slab is simply resting on the beam. You may have several beams like this. The beams may not be even embedded into the slab. These are all identical beams, even though they don't look like identical. They are all identical beams. In this case, still, you may say that, okay, the beams are not really effectively restrained against lateral movement, but typically you don't have to consider the lateral torsional buckling effect because the load of the slab that is coming onto the beam, you can say that there is sufficient friction between the slab and the beam, and then there won't be there is sufficient friction between the slab and the beam top flange, and it will not allow any lateral movement of the beam. Okay, so even in these cases, basically what you are saying is that the slab is providing sufficient lateral support to the beam. But more often than not, you would always have some kind of a connector between the slab and the beam, and when you have that, that is obviously going to be sufficient to prevent the lateral torsional buckling. Okay, any questions so far? We have basically just recapped, revised whatever we have discussed so far in very briefly. Okay, so yeah.
Sir, when you say the slab is resting on the beams, it's not joined. It's just simply lying on it.
Yeah,
Okay, fine.
yeah. So even in that case, you can typically assume it to be restrained against lateral movement. The beams to be restrained against lateral movement, even though you are not providing any special arrangements to restrain it. So theoretically, it can move, but there is enough friction available, and also there is torsion required. Torsion may need the beams to deform a little bit extra because there is slab. So the load distribution takes place in such a way so that uh, the the lateral torsional buckling kind of a mode is not very likely, and therefore you are allowed to ignore the possibility of lateral torsional buckling for such cases. But again, that is not a very likely condition. For some railway structure, I have seen this kind of a beams, this kind of a slab system being used. But the more likely system is where you have a beam and then the beam has some kind of connectors which is welded to the beam, and then it is embedded into the concrete slab, like I have shown here. So these small things that I have marked here, these are called shear studs. We'll talk about composite slabs maybe today or in the next lecture. So these are called shear studs. These shear studs are supposed to transfer the shear forces between the slab and the beam. And then if these are provided, of course, there is no possibility of lateral torsional buckling. Even if they are not provided, you can still disregard the possibility of lateral torsional buckling. I hope that answers the question.
Yes, sir. Thank you.
Okay. All right. So yesterday we saw these two plots. I have just plotted them again in today's presentation, and these, right? So, and this is the summary of in the cases where you don't have to consider the lateral torsional buckling, even though the beam may be unrestrained, right? Okay. And then the question comes, how do we calculate LLT? Because it is LLT that will tell us the value of lambda LT, and that is how lambda LT is the one that governs the lateral torsional buckling capacity of the beam. Okay. So we had discussed this one for a lateral support. So for example, you have this is the beam that you are interested in calculating the capacity of. Let's say I want to calculate the capacity of this beam. Now for this beam, there is a lateral support provided here and there is a lateral support provided here, and of course these are the main supports, and which are also these locations also have lateral supports, but these are the main gravity supports, and then lateral supports are provided here and here. These points don't provide the gravity supports, right? So if I can draw it in 3D, it will look somewhat like this. Okay, so this is the main beam that I'm interested in. I have seen over several years that students tend to get confused between the vertical support and the lateral supports. So wherever they see lateral support, they assume that that place is also providing the vertical support, but that is not really the case. So at this location, at the ends, you have gravity supports. So maybe I can draw it. Actually, what I'm drawing there is a column. So let's say there is a column here. Okay, now I cannot draw the entire shape of the column. Please assume that there is a column here. Yeah. So the beam is coming and resting or somehow connected to the column. Similarly, there is a column flange here to which the beam is connected. Yeah. Some way. So there is some kind of a connection here that is allowing the beam to be connected to the column. And at these locations, the load, vertical load on the beam, that is getting transferred to the column. That means the beam is restrained against vertical movement here. So the beam cannot move vertically downward here. Okay. Similarly, there is a vertical support here at both ends, but there is no other vertical support anywhere else. The beam has only two vertical supports. So in a way, you can say it's a simply supported beam or fixed beam, depending on the type of connection it has. Then comes the question of lateral supports. So what may happen is that whatever system I have here, I may have another system, another similar system. Sorry, it didn't move the whole thing. I may have one similar system a little bit far away from here, and then what I may have is another set of beams. Now, again, I may not be able to draw the entire geometry of the beam, but let's say there is a beam here that is connecting these two beams as an intermediate levels. Okay, so this is the three-dimensional geometry, and then of course there are beams that are connecting these two columns also, and there are beams which are connecting these two columns. Sorry. Drawing a straight line is harder than it may feel. Okay, so now you can see that there are these four beams, right? 1, 2, 3, 4, right? The plan view of this thing is shown here. These are the one, this is one. This is 1, 2, 3, and 4. These are equally spaced four beams. The same four beams are shown here, 1, 2, 3, 4. Is that clear? Now, the vertical supports to the beams that we are interested in. We are interested in looking at the behavior of these two beams, right? We want to know the capacity of these two beams. The vertical supports are available only at the columns. What happens at the intermediate level is that at the intermediate levels where beams 2 and 3 are meeting, the beams of our interest are actually the locations where the load is getting transferred to the beam of our interest rather than vertical support, right? So these locations, so if I look at the beam of my interest, this is the beam of my interest, this beam. If I look at this beam, it has one support at one end, the other support at the other end, and then it has these locations where the load is getting transferred, and potentially at these locations, I'm getting some lateral restraints also, potentially. And we have to see whether we are actually getting it or not. It's just a potential or just a mirage. All right. Is that part clear to everybody? Yeah. Okay. Hopefully, yes. So now what happens is that, let's say our beam here, this particular beam, is about to undergo lateral torsional buckling. So it wants to move laterally, right? And if it wants to move laterally, most likely even this beam, the other beam, this would also be under similar kind of a load, and at the same time this would want to go under lateral torsional buckling. It would also want to move laterally. And if that happens, these braces, which are, I can call them braces, but they may actually be the beams also, number 2 and 3 will not really be able to provide the sufficient lateral support, because if my beam, let's say A, wants to, and this is my beam B, if my beam A wants to move laterally in the middle, so at the ends of course it is restrained, but in the middle it wants to bend, so it wants to move laterally, beam B will also move by the same amount, so that the beams 3 and 2 simply ride on them rather than offering a resistance. However, if you have a slab on top of all of them, then that possibility will be restricted. That possibility will not be possible. That will not be possible. But if there is no slab, these are simply 4 beams like this, then you may have a possibility where A and B can still undergo lateral torsional buckling, and the mode or the deformed shape in that lateral torsional buckling mode will be this. Correct? Which means the effective length, effective unrestrained lateral length, this is your LLT. This is the unrestrained lateral length. It is not LL, it is not original L by 3. So if this was the original L, so LLT will be equal to L, not L by 3. That's what it is saying. So if this is the kind of system you have, if this is the system we have, then the LLT will be equal to L by 3 and not L. Okay. What you can do, however, is, what am I saying? If this is the system we have, our LLT will be equal to L. But at the other end, if we don't have a similar type of a beam, but if we have a very strong wall or some other system which does not move laterally and it is not susceptible to lateral torsional buckling, and these bracings, or this could be secondary beams, which are connecting that wall to our primary beam, in that case, these bracings will be very effective, and they will be effective in reducing the unrestrained lateral length to L by 3. Similarly, if you don't have a wall or something, but you have similar kind of primary beam, so this is your primary beam, this is another primary beam, and instead of just connecting with these bracings, if we go for a diagonal bracing kind of a system, that also is a very effective way of restraining the lateral torsional buckling, and you will reduce the unrestrained length to L by 3. All right. Let me try on the internet and search for some photos that will be, let me see. You must have seen, whenever you see a steel girder in real life, you would have seen some similar kind of bracing systems. Yeah. Let me see the kind of picture I want to. Okay, so I'm showing you one picture at a time. Maybe I'll show you 2-3 pictures. Can you see this picture? Please reply.
Yes, sir.
Yeah, so there are on one pier, for example, you have 2 beams or 2 girders resting, right? And likewise, you can see 2 piers here. So on each pier, you can see 2 girders that are resting, and then the 2 girders together are connected together with some bracing system, right? Now, if you notice it carefully, these are not beams; these are bracing systems which have vertical dimensions, which are a vertical truss, and these are also equally effective, right? But you may remember I had said that if there are only 2 beams and both beams are susceptible to lateral movement, then just connecting the 2 beams together may not be sufficient. But I'm saying here it may work as an effective lateral restraint system. Anybody wants to make a guess why is it possible here, but it was not, that was not the case in the earlier slide? Anybody wants to make a guess?
There the connection might join only the tension part or only the compression part. Here it has a vertical dimension, so it connects both the compression and tension parts and holds it together.
Very good. Yeah. So basically what happens, if you see this, you have to understand this mode of buckling. So this mode of buckling is not lateral buckling alone. It is lateral torsional buckling. So if this was only lateral buckling, so these are the 2 beams. Can you see my hands? So if these are the 2 beams and these 2 beams wanted to move laterally, then this kind of a bracing would not have been effective. But you must realize that the mode of buckling is not this. It is not this. It is this. You understand? It is lateral movement and twisting. So by this kind of a system, this kind of a bracing system, you are effectively preventing any kind of twisting. So as long as you are able to prevent all kinds of twisting, then lateral torsional buckling mode can be prevented. Okay, I hope that makes it clear. So if I had connected only the compression, because compression flange is the one that is likely to buckle, if I had connected only the compression flange, then I was not actually effectively preventing the twisting, because even with twisting, the distance between the compression flanges remain the same. But since this kind of bracing system is provided, it has a vertical dimension. That means it won't allow relative movement between the compression flange on one side and tension flange on the other side, which will effectively prevent the twisting. Okay. Some other pictures maybe. Let me see. Yes, same. Right now I'm getting only this kind of picture. Sorry, I'm not able to get any the other kind of pictures that I was trying to look for. Most of the pictures that I'm getting are of similar kind of bracing. I'll see if I can find some other pictures and I'll try to share with you. Yeah, I don't want to waste time here. Okay, fine. So okay, so going back to where we were. All right, so this is how you determine which is the lateral torsional buckling length we should consider, LLT we should consider. Now, on top of that, we should, like in the case of columns, you remember, there was a role of boundary conditions, correct? So if you had a fixed boundary condition versus if you had a free boundary condition, whether you might have a possibility of partial restraint, and all those things were incorporated to calculate the K value, right? So there was a KL factor. So for columns, you had a KL value, right? And the K value depended on what are the boundary conditions at the two ends. And even if you had partial fixity, the K value could be calculated based on an annexure in IS 800, right? So similar thing exists for beams. Now for the beams, you may realize that the boundary conditions are slightly more involved. It is for the columns, it was simply whether you are allowing a movement or whether you are allowing a rotation or not, right? So maybe I can go to the code first and then. Yeah. So for columns, we had this kind of a table, right? So it depended on whether we are allowing lateral movement at one of the ends, and whether we are allowing rotation or not. Based on those things, the factors K change its value. So factor K was actually it can be theoretically between 0.5 to 2.0, but here it was given between 0.65 to 2.0. Okay, and actually you may have up to infinity. If you are familiar with, I don't know whether this annex was discussed in your compression member discussion. I think annexure D. Was this annexure D discussed for calculation of K for a frame?
Yes, sir.
Okay, so you know that the K value can vary basically between 0.5 to infinity, right? This is the value of, this is the smallest value of K, and this can be the theoretical largest value of K. Okay, so now for beams, however, the boundary conditions are slightly more involved. Okay, so first we will talk about simply supported beams. So simply supported beams are the beams that are supported at both ends, right? And even continuous beams are kind of part of the simply supported beams category, right? So the two different classifications are made. One is simply supported beam. That means beams that are supported at both ends. So these kind of beams. And the other classification is the beams that are fixed at one end. So that is cantilever. Yeah. So even the beams that are continuous over a simple support, right? These are not truly simply supported beams, but even they are come under simply supported classifications as far as this discussion is concerned. Okay. So for the now what happens is that you have to think of since the beam wants to buckle laterally, right? Torsional and lateral. So it wants to, if this was the original cross section, now it wants to undergo this kind of a lateral movement, right? So now what we have to see is that whether the supports that we have, and these need not be these supports only. If you have any lateral supports here, even those supports we have to think of. So let's say I have some lateral supports here and here. So then those lateral supports, whether they prevent only lateral movement, whether they prevent also the twisting, and whether they also prevent warping, correct? So there are three things that we have to worry about. One is lateral movement. The second one is twisting. And the third one is warping. So a particular support may be able to resist one. So if it is not resisting any of these, then of course it does not even count. So for example, you don't have these lateral supports in between, then you will consider this entire length, right? So if there is a lateral support, but it is not effective, like the case we had seen before, then you would not count it. It doesn't matter. That support doesn't matter at all. Okay, but as long as a support is providing at least the lateral movement restraint, then that support becomes effective. Then we have to see what level of twisting it is restraining or torsion it is restraining, and what level of warping it is restraining. Okay, and that depends on how rigidly that support is holding the beam, right? So if the support is holding only one side of the beam, let's say there is a lateral support, but it is connecting only to the compression flange, okay, then it may not be able to effectively prevent the twisting of the or turning of the beam, right? So the beam may be able to rotate about its longitudinal axis very easily because you are holding it at only one place. But if you are effectively holding it from the top and bottom, then it will maybe an effective way. Okay, so that's what we have to see, twisting, and then similarly warping. So you may remember, if I'm looking at a beam from the top and this is the top flange of the beam, warping basically meant that top flange goes this way and bottom flange goes the other way, correct? I think I have exaggerated the deformations a bit too much. So this is the beam, and warping requires that the top flange goes this way and the bottom flange goes this way. Okay, so if we can somehow prevent the rotation, in plane rotation of the flanges, so there can be some kind of a support which will prevent the in plane rotation of the flanges, then we can prevent buckling. So one way to do that could be, if I have a beam, okay, so this is the beam end, and I take a very, very thick plate. Okay, and we weld this plate around So we take a very thick plate and we weld this plate around this beam. Okay, so all this, everywhere we weld it. We weld them together. So that way, the flanges will not be able to move in different directions, right? And that's how we can prevent warping. Other way could be, we can take this thing, the beam end, and weld it directly to the column. Instead of a plate, it could be a flange of a column, right? So this could be just a flange of a column, a thick flange of a column. That will also be effective way to prevent warping. The beam end may be embedded into a wall. That may be an effective way of preventing warping. So based on these, there are several categories created. So you have to go to table number 15 in IS 800. This is how table number 15 looks like, page number 58. Okay, so it gives you two different categories of restraints. One is torsional restraint, the other one is warping restraint. How about the lateral restraint? That is the given, right? If you don't have lateral restraint, that does not even count, right? So then that point of restraint does not even exist, no matter what else you do. So at least lateral restraint is available. On top of that, whether that lateral restraint is also able to restrain torsion and whether it is also able to restrain warping. Okay, so for torsion, you have three categories: fully restrained, and then partially restrained by bottom flange, and partially restrained by bottom flange bearing support. So there are three categories, if you see. One is torsional support, fully restrained. Then the second one is partially restrained by bottom flange support connection. I cannot highlight the bottom flange support connection, and partially restrained by bottom flange bearing support. You understand the difference between the three? You want me to explain? So one case could be that the torsion is fully restrained, right? So the beam is not allowed to. So you have a beam, and at the point, at the location where you are providing the lateral restraint, like the example we saw that picture from the internet, right? So the top flange or the web near the top flange and the web near the bottom flange, they are both effectively restrained. Okay, so this point cannot move with respect to this point. They have to both move together. So if that is possible, that is torsionally fully restrained. Okay, you may have another possibility where you have a beam, but you are restraining only the top end of the beam. Okay, so that is, sorry, it is partially restrained by bottom flange support connection. Okay, sorry. So if you are providing this kind of a connection, this is fully restrained. Other option could be you are using a place where there is a support, gravity load bearing support. So let's say it is sitting on a pier. Okay, and then you tie the bottom flange to the pier. Okay, so in this way you are able to prevent the lifting of one of the flanges. So the flange cannot lift up. And the other possibility could be that you are allowing it to lift up, but still it is resting. So because it is allowed to lift, so this is the third possibility. This is the second possibility. Okay, so both of these, second and third, and this was the first one. So the first one, or in this table, it is 1, 2, 3, 4, 5. First 5. 1, 2, 5. And this is the sixth one, and this is the seventh one. Fine. Is that clear? So first one is the most stiff torsional restraint. Second one is less stiff, but still better than third one. And third is the freest. Okay, and then comes the warping restraint. So warping restraint also, whether you are restraining both flanges, if you look at the first one, both flanges fully restrained. Then compression flange fully restrained. And the third one, there is a mistake here. I had made this correction in my hard copy of IS 800. I don't have it here. There is a mistake here now. So this third one, which says both flanges fully restrained, it is supposed to be something else. I'll get back to you on this one. Then the fourth one, compression flange partially restrained. I think it should be both flanges partially restrained. Compression flange partially restrained, warping not restrained in both flanges, warping not restrained. So basically what it is saying, there are again 3 categories for warping. So these are the 3 categories for torsion restraint. Then there would be 3 categories of warping. Warping both flanges, fully restrained, both flanges partially restrained, compression flange fully restrained, compression flange partially restrained, and flange is not restrained. Not restrained against warping. One, two, three, four, five. Total 5 categories. But you can say that okay, one is focusing on both flanges, the other one is focusing on compression flanges, and the third one is focusing only on both on the possibility of no restraints. Okay, and for these different conditions, it gives you different effective length values. So if L is the distance between the 2 lateral supports, okay, L is the distance between 2 subsequent lateral supports, then 0.7 L is the LLT, effective LLT that you need to use in your equation, right, for this case. Likewise, for this one, you will take 1.0 L. And as you can see, from the top to the bottom, it is becoming more and more flexible, right? And that's how these were placed, these restraints were placed. So as the boundaries become more flexible, your effective length keeps increasing, minimum 0.7 L up to 1.2 L. Okay, and then if you're allowing the partial rotation, then you have to consider 2D, 2 times the depth also, that is added to the length of the effective length of the member. Okay, now there is another complication here which talks about loading condition. So there is a normal loading condition and there is destabilizing loading condition, right? Can you see it? Okay, and what you can see here is that for normal loading condition, your effective length is smaller, but for destabilizing loading conditions, your effective length is a bit larger, right? By how much? How much larger is 0.85 versus 0.7? What percentage wise? Percentage wise, how much bigger is 0.85 versus 0.7? Did somebody answer?
Around 20%.
How much? 20%. Yeah, 20%. Good. So you have to go to, sorry. Read clause number 8.3.2. For beams which are provided with members giving effective lateral restraint to the compression flange at intervals along the span, in addition to the end rotational restraints required in 8.3.1, the effective length for the lateral torsional buckling shall be taken as distance center to center for the restrained members in the relevant segment under normal loading conditions, and 1.2 times the distance where the load is not acting on the beam at the shear and is acting towards the shear center so as to have destabilizing effect during lateral torsional buckling deformation. What is it saying? So you will take, shall be taken as the distance center to center of the restrained member in the relevant segment. Okay, so you will take the distance as per this equation, as per this table, in all the different boundary conditions. But when it is destabilizing, and the definition of destabilizing is where the load is not acting on the beam. Let me highlight this part. Where the load is not acting on the beam at the shear center, is acting and is acting acting towards the shear center, so as to have destabilizing effect. Yeah. Then what do? You take 20% more for effective length, right? So you can see that the values in column number 5 here, they are all 20% larger than the values in column number 4. So 85 is 20% more than 70, 90 is 20% more than 75, 95 is 20% more than 80, and so on, approximately. Okay. So, but did you understand what is the destabilizing effect is from that definition? So, for example, if you have a beam like this, no matter whether it is acting in a simply supported beam or a cantilever beam, if the load is acting here at the bottom, that is away, the load is not acting towards the shear center. The shear center of this beam would be here, right? The shear center of this beam would be here. So if the load is acting away from the shear center, then it is the normal condition. But if the load is acting, like in the third case, if the load is acting towards the shear center, then it is a destabilizing case. Can anybody try to explain why would this be destabilizing case versus the first two cases? It should not be very difficult to visualize. Anybody? No? Why is the third case? There are three cases shown here. The first case where the load is acting at the bottom flange, the second case where the load is acting at the centroid, the third case where the load is acting at the top flange. And the top flange case is called destabilizing force or destabilizing case. No?
Sir, could you give an example where such load condition arises? Because I didn't understand how exactly it acts.
Okay, I'll give you the examples. But right now, can you answer this question first, and then I'll give an example. No? All right. So see, you have to always look at the word destabilizing here and try to figure out stability comes and plays a role here, right? So we are talking about lateral torsional buckling. So if you are talking about lateral torsional buckling, what is the deformed shape? So a beam that was a straight beam before, a beam that is what happened to the pen suddenly? Oh, suddenly the pen has become very, very thin. A beam that is undeformed shape has like a shape like this. If after lateral torsional buckling, it would be shifting laterally and it will be rotating and it will be somewhere here with this deformation. Correct? So if the load was acting here, for example, and that load would be acting here now. Draw a vertical line properly. So the load would be acting here now, right? So this load, if the beam wants to turn this way, the tendency of this load would be, if you think of the centroid of this beam, the tendency of the load would be to bring it back to vertical position. So the beam is twisting this way. but the load wants to bring it back to normal position. Even if the load was acting here, it would not make the beam turn more. But if the load was acting here, then the beam is already turning this way, and the load is going to push it further to make it turn that way. Okay. So as an effect, this is a more destabilizing force, the force that is acting towards the shear center, whereas the force that is acting away from the shear center is not a destabilizing force. Okay. So if the force is acting towards the shear center, then we consider the effective length as a bit larger than the other cases. Is that clear?
Yes.
Yeah. Okay. So now when you have such kind of situation, so let's say you have a beam. I can give you examples from gantry girders, but there will be many more examples, of course. But you must have seen gantry girders, right? How many of you have seen a gantry girder in your life? No? Gantry girder. Okay. You know where the QC lab is in IIT campus? All of you have been to the QC lab, right? The lab behind the civil building, Block B. So in that QC lab, there is a girder. There is a big crane that moves around that yellow-colored beam, big yellow-colored beam that has a motor and it has a hook. And that big beam is resting on two beams on the side. Those beams are called gantry girders. Okay. So if you have a gantry girder, there are various kinds of designs which are possible. So if you say you may have a design of a system which is having some wheels here and then another wheel on the other side of the other flange of the same flange. Maybe I can draw this wheel. If the one wheel is here, the other wheel is here. Okay. And then the two wheels are connected together with some kind of a system, and the whole thing moves on this big beam. Okay. So this kind of a system would require that the load is acting near the bottom flange. Alternate arrangement could be you have one wheel here, one wheel here, and then you have some kind of a beam connecting to them, and the load is applied near the top flange. Or alternatively, you may have an arrangement where you have four wheels, and the four wheels are connected together, and you have a big beam connected to these four wheels. So all these four wheels can be part of a single system where all of them are connected to a single beam, some kind of a beam. Yeah. And if that is the case, you can think of that load to be acting near the centroid. Okay. So I hope it's clear enough, right? So depending on where the center of that load is, so there will be a number of loads acting on the beam. If the center of that load is acting near the centroid, that is the same location as the shear center for an I section, then you can say that it is not a destabilizing effect. But if it is acting towards the top flange, then that will have a destabilizing effect. Correct? So if there is a destabilizing effect, then you have to take 20% larger length. All right. So that is for simply supported beams. I think I'm out of time already. So we will continue discussing about the cantilever beams in the next lecture. Okay. All right. So let me cancel this, close this meeting now. Any questions?
Sir,
Yeah.
sir, in the part where that you showed the diagram of two beams connecting the two other beams which are supported by columns.
Okay, 1 minute. Let me get there.
Yes, sir.
Yeah.
Sir, at the point of connection of beam 2 and 3, what was providing the vertical load there?
What was providing the vertical load there?
Because in the diagram below it, you showed two vertical loads and lateral support.
Correct. So the beam itself is, so let's say this is the system, this is floor system, right? So there may be some kind of an arrangement. Let's say you have some kind of a, if you have a concrete slab, all this issue of lateral torsional buckling itself does not arise, but you may have checkered steel plate or something. So let's say I have come some kind of a system through which I'm applying some loads on every beam. Every single beam is carrying some load. That is gravity load everywhere. Can see?
Yes, sir.
Okay. So now the secondary beams, these are the secondary beams. 1, 2, 3, and 4 are secondary beams, and A and B are primary beams. So what is happening is that for secondary beams 1 and 4, the load is directly getting transferred to the columns. But for secondary beams 2 and 3, the vertical load is first going from the beams 2 and 3 to beams A and B, right? So beams 2 and 3 are resting on beams A and B, and then beams A and B are resting on the columns. So if I draw the free body diagram of beam A, I will see this is beam A. I will see that this is beam A, and there is a vertical load acting on the beam A at these two locations where beams 2 and 3 are meeting them. Also, beams 2 and 3 can potentially provide lateral restraint.
Sir. Yes, sir. Thank you, sir.
Yeah, makes sense?
Yes, sir. Thank you, sir.
Okay. Any other questions, please? Okay, fine. So please, I will upload these videos. Please go through YouTube and again go through the video and try and understand. And if you have some more questions, you can ask in the next class. Okay, our next class will be on Monday, right? Saturday we don't have a class. Sunday we don't have a class. Monday, yes, Monday 10 a.m. Okay. All right, we'll see you on Monday then. And please tell your friends. I'm really disappointed that there were only like 8 students today in this class. It is. Why do I put all this effort if there are only 8 people are going to attend? Okay, so please ask your friends to attend. All right, bye.